Hello, this is the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And here we're in a little mini series for split plot design. And this is part 6 of 10 in that mini series. And I'm going to call it Partitioning the Total Sum of Squares. And here we're going to deal with the model, the split plot model, randomized complete block. So this part of the notation tells us what the first randomization was, and I'd encourage you to watch parts 1 and 2 for more detail on this. But this is the model, and so this first part, of course, deals with the first randomization, and it's a randomized complete block design. And then here's the second part of the randomization for a split plot design. In matrix notation, it can be represented with y equals x beta star plus epsilon, and this piece can be broken into the respective column spaces. So mu, the alpha, beta, gamma, the interaction, and epsilon. Now, as a reminder, epsilon is multivariate normal, mean vector 0, covariance matrix sigma squared v. And look for part 1 and perhaps part 5 for more detail on that. Now, the sum of squares total is always y is equal to I minus j y, and this is y transpose. Sometimes I call it y prime, but it's really I should say transpose. And j is the perpendicular projection matrix on the column space of 1s. Now if we add m and subtract m, where m is the perpendicular projection matrix on the whole column space of x, then we can separate it into this. And as a reminder, m can be broken down into this, and we spent quite a bit of detail on orthogonalizing each of those column spaces, and then this is you add up the perpendicular projection matrices for those different column spaces and you get this. Of course, you can add those again and it boils down to this, but we want to leave it in this setting here because it creates orthogonal column spaces. So for this piece here, what we do is we put this in there. Now notice the j and the j cancel, but everything else is left. So then you can multiply the y's in and you get this, right? That's the first piece. Then you get this. And so this is the sum of squares for alpha, or the first factor, sum squares for beta, the block effects. So this is the sum of squares for gamma, the second factor in your split plot design. We would get the interaction effect, and then I minus m is the error, sum squared error. Now, the thing with split plot, remember in our model, we combine these errors into one. So this is actually both, it contains both the whole plot error and the split plot error, or the subplot error. So we need to split this again into those respective class or errors. So what we do is we take the sum of squares error, so I minus m, and we'll just bring it down here. Now we put in m, remember, which is this. We're going to work with this one and put it in, right? And I'm going to say see part 4 how we derive that. Now we want to add and subtract the same quantity in this. So we add and subtract this quantity. We subtract and then add this quantity, and the rest are already there. So when we add and subtract those and then rearrange, and then we get this, right? So this actually is 100% the same as this. We've just added and subtracted quantities. But now when we multiply the y in to get this piece and the y's to get this piece, These subspaces, if you look at the column space of the design matrix, these are perpendicular projection matrices onto the orthogonal subspaces. So these two are orthogonal, but this is the sum of squares error for whole plot, and this is the sum of squares error for split plot. Now, this is equivalent to that the interaction space, that's orthogonal to the one, it's orthogonal to the one vector, this x alpha column space and the x beta column space. So this and this is still orthogonal to all of these subspaces, so everything is fine. Now, what's interesting, and I say this with pure fascination, all these crazy formulas will match the R software. So when we do these crazy matrix additions and multiplications, it's going to match exactly what R produces. So, and that's it. So now for the split plot model where we use the completely randomized design for the first factor, this was the model, right? So that's a CRD design for the first factor, and then this is the second factor randomization. In matrix form, it can be written as this: y equals x beta star plus epsilon. So it's this, and the error term is multivariate normal, mean vector 0, covariance matrix sigma squared v. And we actually do the same thing. So the sum of squares total is this. We add and subtract m, the perpendicular projection matrix, onto the x. So remember, the design matrix is a little bit different, where it's a different split plot design model. So it's here. Then m for this, the split plot CRD design, m was this, right? Notice there's no block effect. Now, and of course, if you add all those, it boils down to m alpha gamma. But you can put these in this m right here. Of course, instantly the j's cancel, but everything left over is this. And that's the error term. So for the m here, I just went ahead and put m alpha gamma right here. So in this sum of squares for alpha, sum of squares for gamma, sum of squares for the interaction, and that's the sum of squares error. But remember, this contains both the whole plot and the subplot errors. So now we need to split this. So we take the sum squared error, which was this, right? I minus m, but in this case, in this design, it's m alpha gamma. And then we add and subtract this quantity, and we add and subtract this quantity. So going from here to here, nothing's changed, but now we can multiply the y's in, and we get this. And this ends up being the sum of squares error for whole plot, and this is the sum of squares error for subplot or split plot. Now for the full model, and the split plot full model, and this is what is in Montgomery. The model was this, so they put in every possible term. So we have the first order terms, alpha, beta, gamma, and we have all the second order terms, and then we have the third order term. And notice there's no error here because there's a parameter for every observation. So there is no error. So we're modeling it exactly. So it's, in my opinion, way over parameterized. In matrix form, it can be represented like this, where each term gets its own little subspace. And then the sum squares total is, again, y transpose I minus jy. So we add and subtract m. But in this case, m was different. So I'm going to point you back to perpendicular projection matrix. I think it's either part 2 or 3 of this little mini series. So we get so this, we'll get the alpha, sum squares for the alpha effect, sum squares for beta. This is the interaction between alpha and beta. This is the sum squares for gamma. This is the interaction, sum squares interaction for alpha and gamma. This is the interaction between beta and gamma. This is the three-way interaction. And so symbolically we write it like this. And again, all of these crazy matrix multiplications and additions will match what R produces. Okay, well that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks, bye.